Welcome back to G Fun Facts Online. Today we are going to accomplish the impossible. We are going to travel light years away from Earth, zoom in on stars that appear as nothing more than pinpricks of light in our most powerful telescopes, and we are going to map their surfaces in high resolution. We are going to look at sunspots, giant polar storms, and magnetic bands on stars that we can technically never see. This sounds like science fiction, or perhaps magic, but it is actually one of the most sophisticated and rapidly evolving fields in modern astrophysics. It is called spot transit mapping, or eclipse mapping, and it is revolutionizing our understanding of how stars work, how planets form, and what the universe actually looks like up close. To understand why this is such a big deal, we have to start with a problem that has plagued astronomers for decades. It is called the stellar activity problem. For a long time, when we built computer models of stars or tried to analyze the atmospheres of distant exoplanets, we used what is jokingly called the light bulb approximation. We assumed that a star was a perfect, glowing, uniform sphere of gas. It makes the math easier. It works for basic calculations. But it is wrong. Real stars are not uniform light bulbs. They are turbulent, dynamic monsters. They are roiling oceans of plasma governed by magnetic forces that dwarf anything found on Earth. If you look at our own sun, it is covered in sunspots. These are regions where intense magnetic field bundles pierce the surface, suppressing the convection of heat, making that spot cooler and therefore darker than the surrounding area. On the sun, these spots are relatively small, rarely covering more than a fraction of a percent of the surface. But on younger, more active stars, these star spots can be monstrous. We are talking about dark patches that cover 10, 20, or even 50% of the star's face. If we ignore these spots, we get everything else wrong. If we try to measure the size of a planet, or the chemical composition of its atmosphere, unmapped star spots can distort our data, mimicking the signal of water vapor or scattering clouds. To find a true Earth 2.0 and to understand the magnetic engines of the universe, we have to map these spots. But how do you map a surface you cannot see? We cannot resolve the disk of a distant star. It is just a point of light. The answer lies in a clever exploitation of geometry and luck. We use the planets themselves as our cartographers. Imagine a spotlight shining on a white wall. If the spotlight is perfect and you pass your hand in front of it, you cast a uniform shadow. But imagine that the lens of the spotlight has a dirty smudge on it. When your hand passes over that smudge, the shadow you cast changes, because you are blocking a region that was already dark. This is exactly what happens during a planetary transit. When an exoplanet passes in front of its host star, it blocks a tiny fraction of the star's light, creating a U-shaped dip in the brightness graph, which we call a light curve. If the star is a perfect uniform sphere, the bottom of that U-shape is smooth. But if the planet passes over a dark star spot, it temporarily blocks less light than it was a moment before, because it is crossing a region that is cooler and dimmer. This causes a tiny upward spike or bump in the bottom of the light curve. This spot crossing event is a fingerprint. It contains a wealth of information. The exact moment the bump occurs tells us the longitude of the spot on the star. The duration of the bump tells us the physical size of the spot. And the height of the bump tells us the temperature contrast relative to the rest of the star. By observing multiple transits, we can watch these bumps move. If the star is rotating, the spot will be in a different position the next time the planet comes around. By tracking these shifts, we can calculate the star's rotation period with incredible precision, and even watch the birth and death of magnetic fields in real time. This technique has completely surpassed the older methods. Before transits, we relied on Doppler imaging, which looked at distortions in the star's spectrum as it spun. But Doppler imaging only works for stars that spin very fast. Transit mapping works regardless of rotation speed. It provides a spatial resolution defined not by the speed of the star, but by the size of the planet. If you have a large planet, like a hot Jupiter, orbiting a star, you have a high-resolution scanner that can resolve features just a few degrees across. The technology powering this analysis has also seen a massive upgrade. In the early days, astronomers used simple geometric models, literally sliding dark circles around a digital grid until it matched the data. Today, we use advanced software like Starry, developed by astrophysicist Rodrigo Luger. This software uses spherical harmonics, a complex mathematical language that describes patterns on a sphere. It allows computers to calculate the exact light curve for any surface map instantly, allowing researchers to run thousands of simulations to find the most probable map of the star. Recently, this has been pushed even further with the Starry process, which treats the stellar surface as a collection of related pixels, allowing for a realistic, spotty background, rather than assuming a smooth star with just one big spot. This sophisticated tooling has led to some shocking discoveries. Let's look at 3 specific case studies that have changed our view of the cosmos. First, let's talk about the system TOI 3884b. This is a system located about 140 light-years away in the constellation Virgo. It consists of a super-Neptune planet orbiting a small M-dwarf star. M-dwarfs are red dwarfs, the most common stars in the galaxy. In 2025, a team using the Muscat 3 and Muscat 4 multicolor cameras turned their gaze to this system, and the light curves they got back were bizarre. Every time the planet transited, there was a massive, persistent bump in the data. The modeling revealed that this star possessed a giant polar spot. This is a massive cool region, covering the star's entire pole. Now, here is the puzzle. Usually, polar spots are found on stars that rotate incredibly fast, locking the magnetic field to the pole. But TOI 3884 rotates slowly, once every 11 days. This contradicts our standard dynamo theories. Even more surprisingly, by tracking how the planet crossed the spot in different colors of light, the team realized the planet was not orbiting around the star's equator. The orbit was tilted at a wild angle of 62 degrees relative to the star's spin axis. The planet was effectively orbiting over the top of the star, repeatedly crossing this giant polar spot. This geometry suggests a violent history, perhaps a gravitational scattering event with another massive planet in the past, that kicked this world into such an extreme orbit. Without spot mapping, we never would have seen this drama. Our second case study is HATP11. While TOI 3884b showed us the poles, HATP11 gave us a glimpse of a stellar cycle in action. This is a Neptune-sized planet orbiting a K-dwarf star, which is slightly smaller than our Sun. Using 4 years of data from the Kepler Space Telescope, astronomers detected hundreds of spot-crossing events. On our Sun, spots do not appear randomly. Over an 11-year cycle, they start at mid-latitudes and migrate toward the equator, creating a pattern called the butterfly diagram. Astronomers had dreamed of seeing this on another star, and HATP11 delivered. Because the planet orbits at a high inclination, nearly 90 degrees, it acts as a scanner that cuts across almost all latitudes. By mapping the recurrence of spots, researchers found that they were concentrated in 2 specific bands on either side of the equator, just like the Sun. This confirmed that K-dwarfs operate a solar-like interface dynamo, distinct from the smaller red dwarfs. It was the first time a butterfly pattern had been robustly inferred for a star other than the Sun using transits. This also helped atmospheric science. When water vapor was detected in the atmosphere of HATP11b, the team had to be extremely careful. Unocculted star spots can mimic the signal of water absorption. By using the transit map to correct for the spots, they confirmed the water detection was real. It was a triumph of combining surface mapping with atmospheric chemistry. Our third example is the chaos of Corot, -2b. This is a hot Jupiter orbiting a young, extremely active G-star. The light curve looked like a seismometer during an earthquake, full of bumps and wiggles. But within that chaos, astronomers found order. They measured differential rotation. They found that the star's equator spun faster than its poles. But strangest of all, the mapping revealed a forbidden zone right at the equator that was effectively free of spots. This gap is reminiscent of coronal holes on the Sun, regions where magnetic field lines open up into space. The analysis suggested a magnetic coupling between the planet and the star, where the massive, close-in Jupiter might be altering the star's surface activity, potentially locking certain magnetic features to the planet's orbital phase. These findings are forcing us to rewrite the textbooks on stellar physics, particularly regarding the dynamos of M-dwarfs. Stars like the Sun have a tachocline, a layer where the radiative core rubs against the convective envelope. This friction is the engine for the magnetic field, but red dwarfs are fully convective. They have no tachocline. Theory predicted they should have chaotic, distributed magnetic fields. However, the observations of stable, giant polar spots on stars like TOI 3884b indicate a strong, organized dipolar field. The transit maps are proving that in the regime of rapid or even moderate rotation, convective turbulence can organize itself into large-scale structures without needing a tachocline. We are seeing the magnetic engine hit its maximum capacity, a state known as saturation. We are currently in the golden age of this science. But the platinum age is approaching. We have the TESS mission currently building a catalog of mappable stars. We have the James Webb Space Telescope, which offers infrared sensitivity. Since starspots have different contrasts in infrared versus visible light, JWST will allow us to measure the absolute temperature of these spots with unprecedented accuracy. And soon we will have the Plato mission from the European Space Agency. Plato will stare at bright stars for years, allowing us to watch spots evolve over their entire lifetimes and measure the decay rates of magnetic fields. It will also perform asteroseismology, measuring starquakes. Combining internal sound wave maps with surface spot maps will finally link the interior dynamo directly to the surface manifestation. And finally, the aerial mission will likely produce the largest database of stellar surface maps as a byproduct of its survey of exoplanet atmospheres. In conclusion, consider the irony. For most of human history, the stars were immutable, perfect spheres. Even with the telescope, they remained unresolved points. It is a profound twist of fate that the way to see the surface of a star is to block its light. By interpreting the shadows cast by exoplanets, we have gained a superpower. We can resolve features on objects millions of kilometers away, situated dozens of light years from Earth. We have learned that our Sun is just one flavor of magnetic activity, and that the galaxy is populated by stars with polar caps of magnetism, equators of calm, and magnetic cycles that both mirror and mock our own. As we refine these maps with tools like Starry and telescopes like Plato, we are doing more than just drawing maps. We are peering into the hearts of stars, watching the dynamo turn, and understanding the turbulent, magnetic environment in which worlds, and perhaps life itself, are born. The shadow of a planet is not an absence of light, it is a revelation. Thanks for listening to G Fun Facts Online.